record. So in this section, in section 3.3, notice, by the way, this is corresponding to your book, right? 3.3. So I'm not going over 3.1 and 3.2. This is just 3.3. Okay, we're just going to 3.1 and 3.2 was all the trig that I've been teaching you in the last, a few days, that kind of stuff. That's really what goes on in 3.1 and 3.2. So we're going to spend today, we're going to spend tomorrow, Friday, Monday, probably like 4 days on this section alone. Okay, there's a lot to do with it. Your next test, when is your next test? Anybody have it actually open? October 21st? Is that right? That sounds really far. I think that's too far.
No, it's right.
That sounds right?
It's like 1 month, yeah.
I think you said like
You have it?
June 8th or something?
Oh no, 21st. Okay, you know why? I forgot because there's the 4 days of Kairos that aren't in school, so I counted for that. So your next test, I'll tell you now, will mainly be this section and probably the beginning of chapter 4. Like 4.1 and 4.2 most likely. But it's going to be a lot on projectiles. Okay, there's going to be a lot of work on this. Do I have you guys for a double tomorrow, or is the other class double tomorrow? No double for you guys tomorrow? Okay. So your lab will do on Monday. And we're going to do a lab on the computer with projectiles and moving and looking at the angle and change.
Our double's on day 3.
Day 3. They're day 1. That's what it is. Okay. So we've got 3 objectives. First, we're going to recognize when an object is moving in some sort of parabolic pattern or a projectile. Understand the path. And then the third thing, resolve velocities into components to solve by component-specific equations. Okay, and I'll explain what I mean by that in a moment. Okay? So, a projectile is simply defined as any moving object that can be modeled as a point in space. What I mean by a point in space is this. If a rocket is launched, you're not looking at the whole rocket really, right? You're looking at the rocket and you're saying, okay, well, let's look at the center of the rocket, or what we call the center of mass. And then as a result, we can travel or track the center of mass. So the person's center of their body is what we're looking at here. Maybe like, see where the person's belly button is? That's where you would consider that to be like the point. So this is the person's, center of mass right here. And then when they jump, now they're suddenly a projectile. Okay, because they're moving in 2 directions. They're moving vertically and horizontally. So projectile motion here, when we're looking at this, is 2-dimensional motion. It's also free fall with horizontal velocity. So what I mean is this. If an object is only launched horizontally, it's considered a projectile still, because over time, it will start to fall like this. Imagine you have a cliff, and an object is launched off the cliff like this. It looks like it's only horizontal motion at first, but the path that this will take will be this. So in the end, it will be parabolic, it will be projectile motion, although initially it may seem like it's only horizontal motion. Josh, so the path of a projectile that it follows, we said again, is parabolic. Now, what do you think this is trying to illustrate? What do you think the black versus the blue dashed path is trying to show that we could have? Okay, so if it's a higher angle, maybe it follows that higher path. What else? There's many answers that you could think of here. Okay, the motion that you theoretically, not optimal, but theoretical motion versus what actually happens. That's what I was thinking about, and I'll explain that in a minute. What else do you think of when you see this? Somebody heading the ball, yes. Maybe the position, hit them on the head, right? Hit them on the top versus the front of the head, it will go differently. Now, what I wanted to just go over real quick is that the realistic path would be the black dashed line. But in class, what's that?
Is that with gravity?
They're both with gravity, because they're both falling. But the black line includes what kind of resistance? Air resistance, okay? So what we're going to do in physics this year, which you're going to do pretty much in all physics courses until you learn calculus, is we're going to assume that there is no air resistance, or it's negligible. So the path traveled without air resistance is the blue path. Okay, the blue path is without air resistance. The minute air resistance is encountered, it's going to automatically slow down the object. It's going to slow it down so that it would follow that black path right there. Now, if we think about this, realistically in life it's not true. And in life you can have a wind that helps you or a wind that hurts you. If you've ever kicked a soccer ball before, I use soccer because it's a great example, baseball not as much, but a soccer ball, on a really windy day, as a goalie, you always want to keep your kicks down, because if you kick it higher, there's more wind up in the air as you go higher, and suddenly if the wind is against you, you'll kick it and it'll start coming back. It'll drift backwards. So versus, if you keep it low, it won't get affected by the wind as much. So the wind can act against you, or maybe the wind is behind you. And in that half, as a goalie, you know what, I'm going to put a little bit of air in it so the ball will carry further down the field, maybe, depending on what your desired goal is in that problem, or in that play. But remember that air can help or hurt you. We're going to assume that it doesn't do either. Okay, that it is negligible. Whenever I say negligible, I mean it doesn't really affect the problem that much. Okay, it doesn't really have any major impact on the problem. Okay? All right. Let's take a look at this next thing now. And this is where we get our idea of objects launched horizontally. And I need to do a quick little demonstration, so I'm going to steal your desk, Josh and Jen, if you don't mind. You can leave your calculators just moving for now. I'll do this. This is your science. So keep a flip engine. Just click that up. All right. 2 people want to volunteer to do something? It's very simple. Mike, come on up. Jake, come on up. Sorry, Josh. So that goes first. All right, one. Jake. Okay. Now, here's what they're going to do. One of them, it doesn't matter who, because you're over there, you can be this person. So what Mike is going to do is Mike is going to roll the tennis ball off the table. Okay, he's going to take this side, just roll it, and it's going to fall off here. What Jake is going to do is Jake is going to wait right here with this tennis ball. And as soon as that tennis ball leaves the table, he's going to drop his. Okay? And we're going to hope that we see something interesting happen. Back up a second, actually, so we can see all of it. Yeah, so what I want you to do is this. I want you to stand back here, okay? Hold the ball on the table for now. And imagine if you were just going like this, but keep it at the exact height of the table. So don't move the height, like right there. You see what I'm saying? So hold it down and just slide it over a tiny bit till it's off the table. Okay, now wait there. Is he lined up with the table? Is the bottom of the ball lined up with the table? A little bit higher? Okay, and now move left a tiny bit also. Okay. So, as soon as that ball gets to the position right here where it starts to fall, you need to let go of that. Yeah. Make sense? Yeah. Okay, so you're gonna roll it up. When you're rolling it, oops, sorry, you don't have to roll like, you don't have to roll really slow. You can roll, don't whip it, but keep it on the table. I don't want it to bounce. So just like a nice, smooth, look. And you want to go up this side of the table so we can try and see this. You went a little early. Try it. What do you think I'm trying to get to happen? What do you think should happen? Ball? Yeah, it should reach the ground at the same time theoretically. And if we do it where his timing is right, it'll work. Verti's a little bit faster. Ooh. Did you hear only one bounce there? Isn't that kind of amazing to think about? So ready? Think about this, ready? If I extrapolate this idea, if I take a bow and arrow, right, and I pull back on the bow and arrow and I let go, and then I take a BB gun and shoot them at the exact same height and both horizontally, they both hit the ground at the same time. Cool. I mean, obviously with their resistance things will change, but theoretically speaking, if an object is launched horizontally and another one is dropped, they act the exact same way. The time taken is identical. So we're going to take this idea and we're going to use this in one of our problems in a minute. And that's what this diagram is trying to show you here. So Jake would be the red ball that's falling down. That would be like a free fall, and at the same time, Mike launched his horizontally. And what they noticed, and you could actually buy something to do this. You could have something like a spring-loaded thing and launch it at the exact same time. You let go, and you would see this happen like that. But that was the same idea as what's happening. And every instant in time, notice that these all line up. The ball is at the exact same height every single time a snapshot is taken along the way. Okay, thanks, guys. Okay. Very simple, but it's something that we're going to need to know. So we have to utilize that idea. So, keeping that in mind, let's take a look at our first example. Okay, let's go to the next slide and look at the first example there. By the way, it works so much better in this class than the other class. We couldn't get it. It was always like off, like the ball, like boop, 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 boop. There was like a small like discrepancy in it. So you guys got it on the second try. That was good. Very good. So let's say we're looking at a bridge, okay, and it's 300 meters above the ground. And we've got Tom Cruise. He's in another movie that he's starring in. Who knows what it is this time? And he's in this sticky situation, meaning he's got to get away from these people that are chasing him. And he's on the bridge, and he decides he's just going to run off the bridge.
Jump.
Not even jump, just run right off. He realized, he's like, I'm really good at physics. I can figure this out. And I see there's like a platform that's floating, and it happens to be a bouncy castle. And he's like, I want to land on that so I don't get hurt. Floating in the river. So he runs off with only horizontal velocity. Okay? So I wrote he jumps off the bridge, but by running off the edge only in the horizontal direction. So like the tennis ball that Mike just rolled across the table. That's Tom Cruise running off the bridge, just running straight off. He hits the water, and after a horizontal displacement of 50 meters, okay, so he's fallen down 300 meters, and he's gone horizontally 50 meters. And we want to figure out what the velocity is with which he jumps or runs off the bridge. I should say runs instead of jumps. Okay, what is the velocity with which he ran off the bridge? With which he ran, I should correct that for next year too. Ran off the bridge. All right? So, what do we know in this problem? What is something that's given? And you have to consider vertical and horizontal as different things, so specify when you give me answers. Jen, what's one thing you know?
You have VIY, which is 3 oops, am I too far ahead? 300 meters?
That's, you have y.
Yeah.
You said VIY, just y. That's all you have right now is y. So you have y, and what is y equal to? It's not 300 meters, be careful. Yeah, it's negative 300 meters. Let's remember the negative. Simply because Tom Cruise is falling down toward the river, not up. Okay, so the displacement vertically is negative 300. Good, that's one piece. And what else do I have?
Do we know the it's like calling that?
What is it?
Negative 9.81.
I'm going to put AY for acceleration in the y direction. And very good, Victoria. Negative 9.81 meters per second squared. Good, good, good. I know something else. What else? There's another number in the problem. Figure out what it means.
X is 50.
Yep. His horizontal displacement is 50 meters. Okay, let me draw you a quick diagram in case you're confused as to what's happening. So here's the platform. Here's the water. Okay, this is a suspension bridge. Make-believe cables are holding it up. Here's Tom Cruise, modeled as a point in space. He runs off the edge of it, and as a result, ends up falling 300 meters, but ends up going out this way, 50 meters. Trying to make it out the door, sneeze, I don't sneeze. Alright, so he moves out 50 meters and down 300 meters afterward. That's really all we know right now. There's one other piece of information I want to discuss, but I haven't really gone over yet. Remember what we said about air resistance? We consider it to be, what's the word? Negligible. Doesn't really affect the problem. Now, air resistance in these problems would give you some sort of horizontal acceleration. If I'm running, right, and there's a wind that pushes me back, wouldn't that be like a negative acceleration? Or if I'm running down the street and there's a wind behind me, that's like a positive acceleration pushing me. But we're assuming there's no air resistance. So what would the acceleration be in the x direction if there's no air resistance? Yeah, it'd be 0. So here's an amazing thing that we're going to notice this year. Every time we solve a projectile motion problem, we will always use the same formula in the x direction. What formula is the only formula, the only one, that involves no acceleration? There's only one formula that doesn't have acceleration in it, that we've learned so far, obviously. The first one that we did this year didn't have acceleration. What was it? Close, not V over.
Or V is equal to X over T.
Yes, V equals X over T. So we don't know what formulas we're going to use in the Y direction yet, but I definitely know in the X direction, it's going to be something with X over T. 1 second. And let's just call this VIX for now, meaning the velocity in the X direction. Okay, I'm going to pause there.